Welcome back. We were talking about the propagation channel and the signal impairment, particularly microwave signal which is coming from satellite or going up to the satellite, what impairments happen in this propagation channel, and particularly we were discussing about the ionosphere where the effect is very small, and then we came to the troposphere where we were discussing about the percentage of the time the attenuation, how it is shown. So, let us go back to the last slide what we were discussing, that is it is generally available that for a percentage of the average year the rain occurs, and because of that rain at different frequency level what is the attenuation in dB here. So, let us go to the next slide. Let us look at the rain a little more deeper. Normally this let us say this is the ground level, and from the ground level as we go up vertically up in the sky, the temperature is supposed to go down slowly. So, at a height normally at the temperature on the ground level maybe 30 degrees centigrade, and sometimes during summer it may go up higher. As you go up this temperature reduces and it may go to 0 degree temperature, 0 degree centigrade, and below that it will be minus. So, if there are water vapor, that is cloud is present at the, and if there is a formation of water droplets, that will be at higher height, that will be forming ice, and that ice will start melt, that is called melting level, is when it is that 0 degree is occurring. Below that it will be higher temperature. So, at this height ice melt, this is very ideally shown, actually this height varies, but generally thumb rule is about 4.5 kilometer to 5 kilometer vertically up. This is the melting layer or 0 degree isotherm, people call it different names, but it is at this point 0 degree. And when the rain occurs or due to some other reason in the atmosphere, if the temperature is lower, this height may come down during the rainy season, monsoon season, this height may come down to 4 kilometer or even lower, but that depends on place to place and environment to environment, season to season, etc. This is just some formula we are showing. Ideal case, let us take at a height h the melting level is occurring, and from the ground level a signal is looking to sending to the satellite at a elevation angle theta. So, it is not the direct vertical height, it is the signal how much length it is passing through this water, and this green this blue area is rain. It is, let us assume it is fully covered by the rain. It may happen only part of this signal is passing through rain, rest of the part at this height even is not passing through the rain. Those are different cases. I am taking simple case where it is a stratiform rain. So, rain attenuation depends on the signal path passing through the rain and the attenuation per unit distance, per unit kilometer, how much is the attenuation. It is based on the that you can calculate the rain attenuation. Simple formula, that is that A0, that is attenuation for 0.01% of the time, that 0.01 you know the rain rate we have talked earlier, is equal to gamma of 0.01 into LE. What is gamma? Where gamma is called specific attenuation, that is in dB per kilometer. How many dB per kilometer for 0.01% of the time, what is of the rain rate. So, gamma of 0.01 has to be written, and LE is that length, slant length through which the signal is passing through the water, that is the rain, signal path length through the rain. So, let us do a very quick calculation to understand the numbers, that is assume that is elevation angle of 35 degree to the satellite from ground station, and the rain height is 3 kilometer direct vertical height, at 3 kilometer the rain is occurring, and specific attenuation for this particular rain is gamma is 0.01 is equal to 2 dB per kilometer. So, find A, that is attenuation 0.01, A, find A. Assume rain is homogeneous as we have shown in the last picture, over the complete signal path, which is named is stratified form of rain. So AR is equal to that attenuation due to rain is 3 by sine 35, because of that angle, that is the hypotenuse, multiplied by 2. So it is 10.46 dB. You can see, though it is 2 dB per kilometer, because of this 35-degree angle, you are getting 10 dB attenuation. Now let us look at this this unit, that is this parameter, that is gamma. For what this gamma depends, which is 2 dB per kilometer. If this increases, the whole thing increases. If this decreases, the whole thing decreases. This depends on frequency, polarization, etc. So specific attenuation is modeled as a power model. Is there are two constant k into rain rate at 0.01% of the time to the power alpha. The k and alpha are two coefficients, where gamma r is the specific attenuation of the rain, and r, capital R 0.01 is the rain rate for 0.01% of the average year. So this k and alpha depends on the frequency and polarization. The details are available in the book. So it just to give you an idea that it varies based on the polarization and the frequency, and of course the rain rate, the gamma r will change. Now what are the other possible attenuation other than rain? There could be gaseous absorption. You know, air is a form with gaseous, which is oxygen, maybe water vapor also in the gas form of water. Then it's been seen that absorption due to water vapor is maximum at some particular frequencies, that is at 22 gigahertz, at 183 gigahertz, 325 gigahertz, etc. And absorption due to oxygen is maximum at 60 gigahertz, 118.75 gigahertz, etc. Water vapor absorption varies with temperature and humidity, that is obviously. And there is water vapor is another form is cloud. So it is caused by liquid water content in the cloud. And there are certain plots which people have experimented and plotted vertically above the sea level, that is at a particular pressure, temperature, and water vapor content of that. There are two curves shown here, H2O, that is a water vapor, and you can see the x-axis is frequency. This is 10 gigahertz, this is 100 gigahertz. So this is the range where we are normally operating in satellite communication. So you can see that is 0.1 dB per kilometer. And then at some point it peaks, then it lowers down and then goes up again at a higher and higher frequency. Similarly, oxygen peaks around 60 gigahertz, first peak, and then subsequent peaks are there. So these are people have experimented and plotted. These can be taken as some numbers for calculation or initial estimates. Here I have shown some other plots, that is percentage of the total time attenuation due to cloud and fog. Again for this different frequencies, 12 gigahertz, 20 gigahertz, 40 gigahertz, etc. So there are these different plots of fog in dB, but you can see the values of the dBs are much lower compared to the rain at a different percentage of time at different frequencies. Then atmospheric impairment includes the melting layer attenuation. At certain height above ground, snow and ice precipitations are melted into rain precipitation. We have already mentioned this one. Region around this height is called melting layer. Melting layer attenuation is significant during the light rain and low elevation angle, etc. There is effect is a sky noise increase. Energy absorbed by these hydrometers are emitted in wider spectrum as black body radiation, in increasing the noise power in the signal path. So it absorbs the energy and re-radiates and all over the big spectrum. So it is black body radiation with a increase in noise power. And signal scattering by hydrometers also add to the noise. They scattered from other particles add to I can say noise, it's actually interference. Then other interference, other effect is signal depolarization. We have seen raindrop depolarization, differential phase shift and differential attenuation caused by non-spherical hydrometers caused signal depolarization, we have seen. And it creates cross pole interference in orthogonal signal component, obviously, because your polarization has changed. So the cross polarization effect will be there if there is a orthogonal polarization communication going on in the same path. Then there is something like ionosphere scintillation. Troposphere scintillation can also occur with a small bubble like thing where higher density and perturbation in a smaller region for smaller time. So, this variation of magnitude and profile of refractive index causes signal amplitude and phase fluctuation. This scintillation depends on the length of the signal path and antenna beam width, etc. How much signal. If the antenna beam width is very large, then scintillation effect is very small. This scintillation is very fast, so therefore you can see the times are shown in hours here, and you can see the attenuation is fluctuating, sometimes very high, again low, high, low. This is very important because we are not really communicating, though we see availability of the signal over the year, we can guarantee, but we have to see the effect of the signal in a very short period of time, that is a few seconds. A very important event is going on and you are watching in the TV, and suddenly the signal gets disturbed for a few seconds. That is disturbance. But if you see in the over the average year, then it will be very small time. People may say, oh, you. But if there is important event going on, you may miss. You might miss that boundary hit by Tendulkar or Virat Kohli. Just at that moment, signal get lost. So, you will be irritated for that, but your service provider may say that over the average year it was only few seconds. So, it is very important depending on the purpose you are using the communication for. Okay. So, there is other possibilities are intersystem interference, that is there could be a terrestrial or two neighboring satellite systems sharing the same frequency band. We have seen the C by I effect in the last period due to the overlap of part of the main lobe or the side lobes based on the antenna gain, and cause differential rain attenuation caused by differential rain attenuation at the different signal path. So, they can scatter and interfere, and a large reduction in the desired signal and small reduction in the adjacent signal path. So, there are possible of intersystem interference because of the rain which is coming, and that cross pole discrimination could be are plotted. These are all again average numbers people have taken and based on certain experiments, that is percentage of time. You can see very low percentage of time, and the cross pole interference is quite high at two different frequencies. So, there are combined effect of oxygen, water vapor, cloud, rain, scintillation, etc. Some of these phenomenons are correlated, some of them are uncorrelated. So, there is a model people say the total attenuation because of them can be framed as attenuation due to oxygen plus attenuation due to water vapor plus attenuation due to cloud and rain square plus attenuation due to scintillation square, and the whole thing square root of that. This is a certain model people have done, and this is a combined attenuation model, and a rain out of that is most dominant for our frequency of interest right now. So, let us go a little more deeper, and that is in a clear sky operation, really what happens to our signal, what happens to our EIRP and G by T. So, let us see, the power received in dB is what is transmitted, that is EIRP with the gain of course. So, EIRP and the receive antenna gain and free space loss, and this is in the clear sky, there is no rain, and during rain power received in dB will be same EIRP, receive antenna gain minus free space loss and minus loss due to atmospheric impairment. Now, this plus minus all these things when we are talking, it is in dB, you have to remember that. So, something is adding, that is loss due to atmospheric impairment. So, we have to mitigate this, that is called fade mitigation technique or FMT, that is used to restore the link from the short duration outage. Just now we talked about that Virat Kohli hitting a 6, that short duration outage when the atmosphere loss exceeds the established link margin. So, that is the fade mitigation technique. It could be for longer duration also, but many people are interested in this short time mitigation. So, objective of the FMT, I put it in a slightly different way. You just see C by N naught is C is EB into RB, is energy per bit into the bit rate, energy per bit into bit rate. So, EB by N naught into RB. Now, after FEC and coding and modulation, that FEC is forward error correction, there is a forward error correction coding, error control coding, which improves the errors. After FEC coding and modulation, bits can be grouped into symbols. So, this RB can be called as RS. So, it is a symbol rate instead of bit rate. So, EB by N naught we can call it ES by N naught, and RB can be called RS. So, C by N naught can be stated as ES by N naught into RS. Now, let us look at this one, very important. This is in ratio C by N naught rain is a C by N naught clear sky reduced by rain attenuation, A rain. This clear sky is now reduced. So, you get C by N naught rain. So, we have to go back to this. So, we have to counter the effect of A rain. So, objective of FNT is to mitigate the effect of A rain. So, fade mitigation can be done in various ways. That is, again we go back to that C by N instead of N naught. C by N is ES by N naught into RS by B. B is the bandwidth. So, N naught into B is N. Options to mitigate the effect of A rain is to improve the left hand side C by N, and that is done by power control. You can improve the right hand side, that is called signal processing, and you can use a completely different link which is unaffected by A rain. So, it is called diversity, or you can use it different time, then it is layer 2, that above the physical layer, it is called automatic repeat request, etc. So, there are various possible techniques to mitigate that. We will let us see one by one, we will see. So, all mitigation techniques needs additional resources. We have to remember that any mitigation technique we do, additional resources are required. How much? Let us see. Let us see with short term rain effect. There is a fade depth in the y axis, and this x axis is the time, and this is a plot available from a paper. You can see that with time there are some precipitation is occurring and no precipitation, that is inter event, there is interval, again precipitation event is occurring. So, whenever precipitation event is occurring, it is going above the higher fade depth. Higher fade depth means poor attenuation. So, you can see, but this is not constant, it is varying over time, sometimes it has come down, sometimes it goes up. So, these are called fade episodes, and there are certain interfade interval. So, during the precipitation, when the rain is occurring, there may be small breaks or reduction of the total water content that is falling, and this duration is called fade duration when it is above certain fade threshold. So, up to this fade threshold your system is able to operate, this much attenuation is able to take, beyond that we have to take care. Now, function of fade countermeasure or mitigation is, first you monitor the BER or C by N, then that is possible with the open loop, that is transmitter monitors its own reception, the transmitter monitors its own reception. So, the transmit path is what is happening, he knows that is going to satellite, and satellite is rebroadcasting back. So, some power is coming back to the satellite, assuming the transmitter receiver whole thing is both are in the transmit receive antenna gain contour of the satellite, coverage of the satellite. And it could be closed loop, that is transmitter gets a feedback from the receiver, that how much receiver, that means uplink and downlink both towards the receiver is also known to you. So, you estimate the next state, first you monitor and estimate the next state, and then real time prediction of the algorithm is needed, because real time you are doing, and because you have to predict what is going to happen, and accordingly you have to take a countermeasure or mitigation. So, control loop changes the link state using the fade mitigation technique, which could be local control loop, or which could be protocol to modify the remote station configuration itself, because if it is happening in the downlink, you have to modify the remote station configuration. So, power control is done by the by a technique, let us say how it is done. C by N clear sky is ES by N naught in RS by B, that is the required PER corresponding to this ES by N naught, and during the rain C by N during rain is clear sky C by n is attenuated by 1 by rain, it is in ratio, it is reduced PER because now the whole C by n is reduced. So, we have to multiply by A, so that you get back the required PER, C by n during rain multiplied by A. So, that means A time attenuation which was happening, that has to be that C has to be increased by this many dB, A dB, okay. Though it is shown in ratio, this much amount C has to be increased by this much amount. So, by C by n power control, we mean that C by n power control is C by n rain multiplied by A, or in dB it will be plus A. A is the attenuation due to rain. Shown in a different way in the picture, that is it's as if it is a satellite is transmitting and ground is receiving. So, power received at the station is PR, and the same equation PR is EIRP of the satellite plus the gain of the receive antenna minus path loss or free space loss minus the attenuation A, and receive power at earth station is reduced by rain attenuation. But then some more things are happening, let us look at it carefully. That is, rain absorbs the microwave signal and it raises the rain water temperature. So, some energy it has absorbed. So, rainwater temperature has increased slightly. You can say the effective noise temperature of this lossy medium, because it is a absorbing thing. So, it is a lossy medium. So, this lossy element effective noise temperature has increased. That means, this receive antenna temperature, which was looking at clear sky only and getting the brightness noise or background noise from the clear sky. Now, in addition to that, this is also added. Actually, background noise will be reduced by this much amount because it is a loss, but something will remain, and this loss is introducing, it has its effective noise temperature. So, it is giving some more noise. So, the effective noise temperature of this element is increasing, and that will increase the antenna noise temperature. So, let us say without rain it was, so antenna noise temperature increase means receiver noise and antenna noise temperature together is system noise temperature of the receiver. So, that is Ts. So, without rain let us call it Ts clear sky, and with rain during rain it is called Ts rain. So, Ts rain is more than Ts clear sky because temperature has increased, effective noise temperature. So, the receiver effective noise temperature has increased, system noise temperature has increased during rain. So, what is happening because of that? Because of the receiver system noise temperature that is increased, and that means that receiver G by T is decreasing, because receiver gain is antenna gain, G remains constant and T has increased during rain. So, two things have happened. One is the signal power has been reduced, and that is G by T has decreased. So, double effect. So, therefore, your C by N naught in clear sky, which is EIRP plus G by T clear sky minus free space loss minus K. Now, with C by N rain, C by N naught rain, it is EIRP plus G by T of rain minus A rain minus LFS, that is path loss or free space loss minus K. So, EIRP is reduced by A rain and G by T is also reduced. So, double effect is happening because of that. So, FMTs are realized, that is phase mitigation techniques are realized in 4 different ways: power control, uplink, downlink and beam shaping, and signal processing or waveform adaptation keep the constant BER by changing the coding, modulation or data rate. We will discuss these things, as well as there is diversity, that is site diversity and satellite diversity and frequency diversity, and could be layer 2. These 4 different techniques we have briefly talked earlier. So, let us quickly go through the power control FMT. They increase the C by rain, A rain times, that is whatever attenuation has occurred due to rain. Uplink power control to increase the earth station power. If I increase the earth station power, what happens? Or it could be increasing the downlink power, that is from the satellite power, or it could be done by beam control, that is increase satellite EIRP at affected area by antenna beam, that is the gain of the antenna, transmit antenna I increase, so that EIRP increases over that area, focused area. You can see the uplink, there is some rain, I have shown here cloud, there is rain, and downlink also there is some rain. So, uplink power control, it operates at larger output back off during clear sky. You know, output back off, if you remember, that was non-linearity is coming, you have to operate in the non linear region. So if you have to increase the EIRP, you will suddenly get into the nonlinear region. So therefore, in the clear sky, you have to operate with a larger output backup, so that even during day when you increase the EIRP, it does not exceed the linear region and enter into the nonlinear region. Now, the oscillation power is increased by reducing the output backoff, and it can compensate both for fade in up and down link. The possible problems because of that is, because you are increasing the power, adjacent channel interference in the multi-carrier operation can take place. That can be shown like that, that you have, this is the different transponders, which is adjacent channels. This is the frequency x axis, and y axis how much is the power you are operating. Now, this type of segmentation or transponder separation we have seen in the spacecraft discussion. Now, one of the transponder, if I go on increasing the power, so it's some of the power will fall more, will increase more and fall into the adjacent channels or adjacent transponder band. So that's called adjacent channel interference. Pictorially it is shown here. So similarly, adjacent satellite interference can occur, nearby satellites. And possible problem in the downlink fade is this is that nonlinear curve of the satellite. So you, to operate in the linear region, you have to give a output backup. So when you jack up the power this side by increasing the input power, it should not enter into nonlinear region. So initially you have to operate more and more lower region. So that means your output power will be much lower. So with less output backoff, intermodulation products at satellite, I mean, if you give it less, so there will be intermodulation product due to nonlinearity. And downlink power control increase the satellite EIRP, single carrier operation. If you increase the satellite EIRP, this intermodulation does not occur when it is a single carrier operation, that is TDM or TDMA, which is less affected. Our satellite TV broadcast is normally in TDM. Possible problems could be increase in intermodulation product if there are multiple carriers, and interference due to service area of the adjacent satellite or terrestrial network, because you increase the power where the rain is not there, where there is clear sky, the area which is seeing clear sky and satellite power is going there, here increase satellite power. So it will have the effect on the terrestrial network, or it will act as a C by I to the adjacent satellite operator. That C by I we have discussed earlier. It could be done by spot beam shaping, that is increase antenna gain towards the affected region, use adaptive beam forming network. No ill effect of the amplifier nonlinear region, because you are shaping the beam only, not the amplifier you are changing. You are increasing the EIRP by gain control of the antenna, and futuristic technology. You need onboard processor, etc. Now let us go to the signal processing FMT from the power control FMT. This is the second technique. This is done in our regular operation of satellite broadcast. Let us see what it is. C by N in the clear sky is, we have seen this expression ES by N naught into RS by B, that is for the required PER. For C by N in the rain, C by N in the clear sky into 1 by A rain, is in ratio. So this will give reduced PER for the same ES by N naught. For the same ES by N naught, it will give the reduced PER. But if I change this ES by N naught, we get a different PER. Reduce the ES by N naught into R by a factor of A, and you get the required PER. How? And that is code rate or modulation or data rate change. Let us look at it. For you are aware of this curve, that is ES by N naught versus symbol error rate, or EV by N naught versus BER. And for different type of modulation, say BPSK to higher order of PSK, here this is taken from a paper which is showing BPSK 4, QPSK 16 QAM, 16 PSK, etc. You can see for a particular BER, when you go for higher order of PSK, you need higher ES by N naught. That means you need more power. Say let us take BER 10 to the power minus 4 or symbol error rate 10 to the power minus 4. For the BPSK, the amount of ES by N naught is required to get this error. for QPSK you need more ES by N naught to get this error. To 32 phase PSK you need much more. So, this higher order PSK you get the advantage of spectrum efficiency. In one symbol period you can push more bits, that is the advantage, bandwidth advantage you get, but you have to give more power to reach the same BER. Now, what happens that say normally clear sky operation you are operating at this with a higher, because of the rain you have attenuation of this much, say 15 dB attenuation you have. So, instead of increasing 15 dB you start operating at lower PSK, at a lower order of modulation. Your spectrum efficiency you have to sacrifice, but you will get the same BER by reducing the ES by N naught or EB by N naught by changing the modulation scheme. By changing the modulation, same thing is for coding, channel error coding also you can do the same way. It is called adaptive error coding and modulation. So, channel coding, what is done is additional bits are added to improve BER at lower EB. You need larger bandwidth obviously, and use simple coding at normal time, use the full power code during fade. Okay. So, you can increase the bandwidth and you can get more error correction when the fade is occurring. So, that is the way of channel coding. So, interleaving can be can be used to distribute the burst fade due to loss. Say a short fade is there, normally these error control techniques they cannot take care of the burst error, they can take care of the random error. So, distribute that burst error into a random error, you can use the technique called interleaving, and turbo codes are most suited. People use LDPC coding also. So, with this we close for the time being, and we will continue the discussion in the next period. Thank you very much.